Good morning, teachers. This is Bidit Kalita from the Department of Mechanical Engineering. Bearing roll number MEB19008. Today I'm going to simulate the flow that takes place through channel whose cross-section area suddenly changes. We will do it using Ansys. So let us open Ansys workbench. The interface looks like this. Now we will draw the fluid flow fluent tool from the toolbox to the workspace because this is where we will do most of all our stuff. So as you can see, the part here first tab here is geometry, because the first part in simulating this kinds of problem is creating a geometry, whether importing it from other sources or creating it ourselves. So we will create it ourselves. Before creating the geometry, let us look at the diagram or the channel. So this is what the channel looks like. As you can see, the channel is symmetric with respect to this axis, and since we are simulating the flow for the bottom part of the channel only, we will draw the geometry for the bottom part on. So let us, right. Now we can draw our construct geometry in space claim and design modeler. We can choose any one, but I prefer design modeler. So let us open design modeler. Let us wait for it to load. Okay, this is the design modeler interface. So we will choose a plane to draw or sketch, where we will draw our sketching. Now let us, now what could I have done is I could have simply joined these 2 points using a single line, but as we can see from the problem, this though it looks like a rectangle, now it is a rectangle, but as you can see, this upper part is a velocity inlet and this is a wall. These two are different entities, and for just for the sake of a simple understanding by the software, we will describe this edge by two lines instead of one, so that there are no inconvenience created during the modeling. So as you can see, these two lines are not parallel. These lines are not parallel. Let us make sure that the lines are parallel. So now it is parallel. Let us specify the dimensions. Check that. H1, this is V2, this is V3. So, dimensions. As you can see, the length is 1 meter, half of the channel height is 0.1 meter, and half of the inlet height is half of 0.1, that is half of capital H, which will be 0.05 meter. Specify. Ground has become small. So we will zoom in. Okay, as we can see, these points are not uh, connected. That's because there must have been some error while drawing the line, because these 2 points did not coincide. Let's coincide these points, this point and this point. Okay. Now it is done. Now it is done. Now this is what our outline of our geometry looks like. Now how do we convert it into a surface? Go to concept, surfaces from edges. Here you can see the plus sign because it means that there is a sketch or there is some elements in that XY plane. Here is a sketch one. We will select the sketch. As you can see by the yellow line, it has been selected. Apply, generate. So this is essentially what our surface looks like, or geometry looks like. So let us close it. The second step is, as you can see, is meshing. As you can see by this icon, it means we are ready to edit. The tick sign means that it is done. The computer doesn't know that whether we are done or not. It means that it is ready enough to go for the next step. It does not know whether our work is done or not. Okay, please take this time to load. This is a genuine software downloaded from the company's website itself, but this software just sometimes randomly crashes. A genuine software, not even a cracked software. Let us now look. Let us now look as this is the geometry. Let us now see what the unedited meshing from the computer software looks like. It looks like this. It is essentially just simply dividing the surface into small squares, but these elements are not small enough to do near to accurate simulations. So what we will do, we will change the size, we will change the shape of the mesh. How do we do that? Let's go to insert, sizing, select the edge. Let us choose this edge. Means I'm working on this edge, as the yellow sign shows. I'm working on that edge. Now the type element size means that we will specify the element size. As you can see in this, the default value is also given, but we will not work like that. We will use the method of specifying the element size using number of divisions. By dividing the edge into number of sides, we will do the simulation. Essentially it means that we are defining the number of size of elements by dividing the edges into some small parts. We don't need any bias here because it is a very small edge. The dimension is not that high. So let us do for another edge. So, we are working this edge now. Again, similarly, number of divisions. And this length is greater than the height, so we will have to choose a bigger number. Let us choose 120. We can choose 123 as well. We just need to select it suitably. Now here we need bias. This is a bigger length, and we are concentrating our studies. We know that most of the thing happens on the left hand side near the rapid change in area only. So we will select the bias. This we will select this bias. Let's change the bias factor to 4. Okay. Let us do for the other edge. Apply. Size number of division. Again, we can choose 120. We can choose 150. Let's choose 150. Now here we will use reverse bias. And for the remaining two edges, we have select sizing. As you can see, two edges has been selected. Okay, number of divisions. No bias is needed because this is a small edge. Now let us go to method and change the mesh shape. Now if we update it, we will see what the edited meshing is there. From the simple squares, this is what it looks like. See, these are very small elements. The smaller the elements are, the more accurate the simulation will be, given that we do not do any other kinds of mistakes. Now what we will do is we will name the edges. As you can see, name selection. As I said in before, that this upper part is a symmetric to, it is a symmetric line. So we will name it symmetry for this edge. The top left edge is the inlet, and the whole of the left is outlet. We can also name this outlet. And the lower edge, not only this but also this edge are wrong. So we'll choose this edge. This is the velocity. Okay, now as we can see that there is a update sign here. It means that we have done something after doing some other editing also that has been not been saved. So before going out to setup, we will update. it is ready to go to setup. It was ready before as well, but we didn't edit or save the nomenclature of the edges. So open setup now. Let us hope it does not crash randomly. As you can see, this shows the inlet as we have specified it to be inlet. It shows inlet. If we have not nomenclated it inlet, it would have not shown these arrows. As you can see, it shows the half-lit by arrows. We will have to do a lot of tweaking here. So let us go to general. Here we don't need to change anything because everything is the way it should be. Pressure base, absolute, steady, planar. But the model is laminar, and it would be a viscous flow since there is viscosity related. Viscosity is yes, viscosity is yes, laminar flow, viscous laminar. Materials, I think it is air. Is the density? Sorry, is the density? Density was 200. Viscosity is 0.1. Density is 200. Units are same. So same. 1. Change, create, close. Solid is aluminum. We don't need to change that because nothing is given to us. Okay, the velocity magnitude was 1 meter. Close. Okay. Next, we need to go in solution methods. This pressure velocity coupling. The scheme will be simple. This pressure will be standard. This second graph, it is okay. This calculation. These parameters remain the same. Initialization. No, before initialization, let us check if these plots have been. Yes, these are on check already. So residual basically means the level of accuracy this simulation is to analytic solutions. Okay, so let us go to initialization. It will be standard initialization with all the initial values set to 0. Let us initialize it. Contours of pressure. Shear stress. Shear stress. Skin friction. Let us check this because we need to make it. If we do it after we do the calculation, this tab simply just closes off. Yeah. Let's do the wall. before doing initial IPA, let us go to calculation now. Number of iteration basically means the number of calculation it will do repeatedly. Just check it 2000. Reporting interval, it is after how many iterations do we change, do it reports the results. So let us type the results have been uploaded here. You can see this graph has been on display. We now zoom it. Now, as we can see, this is the skin friction coefficient. As we changed it to contours of wall fluxes and chose skin friction coefficient, we need to do. I had to do it before getting the results, because after going on results, it does not simply opens after you come back to do the skin friction coefficient. So before calculating the results, I have tried to show before going into the other velocity profiles and pressure profiles, I've tried to show you the skin friction coefficient, which basically looks like this. So it's done now. So let's go back. Let's go back. Let's go back and see the results. See the I was skeptical if the skin friction tab would show up. It simply did not show. Now this is the wireframe. As you can see, the surface is not showing this because this is the wireframe. You can see this is the selected. Now let us first see the velocity profile. For that we need to go to contours. Now we can go from this shortcut as well, or we can go from insert as well. Let's go contour 1. Okay, all domains. Yes, it is all domains. Location will be symmetry 1. Variable will be velocity, obviously, because we need to see the velocity profile. Let us select it. As we can see, there are some lines. This is the velocity profile. You can see some lines, which means there are some roughness in calculation. But if we increase the number of contours, this will see the lines. Let's remove. This the number of detail will be high, level will be high. So the velocity profile has been done. So let us next look for velocity streamline. For that we need to go to streamline, or we can also go from here as well. So streamline. Okay, all we don't need 3D streamline. We need surface streamline. Again, symmetry 1. Let us choose the number of points to be 50. Velocity will be the variable again, because we are looking for streamlines. Now as you can see, nothing looks changed here. That is because this contour 1 is selected. Contour 1 was the velocity profile, the stream, not the streamline. If we uncheck the contour 1, then we can see the streamline. Now let us go again back to, if you uncheck it, we can see the wireframe. Now we need to take out the pressure profile. For that again, we go to contour 2, all domains, symmetry 1. This time will be the pressure will be the variable. Just change the level contour to 30. This is what the pressure contour. This is what the pressure contour looks like. So this is the pressure profile. This is the streamline profile, and this is the velocity. And I've already shown you the skin friction coefficient near the wall, 5. So this is all from my side. So this is my solution. This is my method or the procedure that I followed to attain the solution to the problem. So